Hello everyone, welcome to iitiansgateclasses. So in today's session, we are going to see your state space analysis. Okay, so this will be the last session in this control system subject. So let us then begin today's session. So state space. So up till now, whatever we have read, okay, whatever we have seen. So all those things is basically for single input, single output system. Or you can say basically the classical control system, it is based when a system has only single input and single output, max to max. If it is your two input two output system, we can analyze the system very easily. But what happens if there are multiple inputs and multiple output in the system? And one more thing that we have seen in your classical control system is that for analysis of classical control, we require your transfer function. Okay, transfer function, and transfer function can be written only for LTI system, okay, linear time invariant system, as well as causal systems. Okay, you cannot write for non-linear or time varying system or non-causal system. But in state space analysis, we can even analyze the system, those are non-linear as well as time variant. Okay, so this is one of the most important advantage of analysis of a system using state space analysis. And one more thing is that as there are means for writing the transfer function, we know what initial conditions are always zero. Okay, we always consider that the system is what, its initial state is always zero. So we can never get the zero input response. Okay, zero input response or the natural response of the system we can never get. But with the help of state space analysis, we can get both your zero input response as well as your zero state response. Okay, and one more thing is that means in a system that we are analyzing using the classical control system, we only get the idea about your whatever input we give, we get the corresponding output. We never have any information about the internal state of the system. Okay, we never get to know what are the internal state of the system, that is not known to us. So now in the state space analysis, we can even get what, we can get the internal state of the systems also. Okay, so these are all the advantages of your state space analysis. Now how do we basically represent using state variable method or state variable analysis? Let us see that. So first let me write the expression. So these are all represented in matrix form. So first I will write the matrix form, and then I will also write the order of the matrix. Okay, so now over here if you see, so this X dot or X matrix, okay, so X matrix, it is basically known as your state variable matrix, or you can even write state variable vector also you can write. Okay, so state variable matrix or the number of states in the system, let us denote it with n. So this matrix X dot has your order n cross 1, and even X, as this is basically the differential of your means X dot basically describes the differential of state variable, so this also has n cross 1. Now let us assume U is basically what, U denotes your input matrix. Okay, input matrix or input vector. So number of input, let us assume as your m over here. Okay, so U is basically what, input vector and number of inputs is equal to m. So this is m cross 1. Okay. So now if this is n, so that means A has to be means order should be n cross n, and B should have order n cross m. Okay. To keep your equation satisfied, we need to have this. Now y is what? Y is your output matrix. Okay, output matrix, and the number of outputs are, let us assume p. So this will be p cross 1. Okay, and x is already what? N cross 1, and u is m cross 1. So accordingly, let us write for C and D. So I haven't defined what is A, B, C, D. Let us first write the order. So this will be P cross N, and D will be what? It will be P cross M. So now you can see this expression will be satisfied. Now what are this A, B, C, D matrix? Okay, let us see one by one. What is this A matrix, B matrix, C matrix, and D matrix? So let us talk about it. So first you can see A matrix. So it is n cross n. So A matrix is basically known as your system matrix. System matrix. Now why this is known as system matrix? Because with the help of this matrix only, we are able to know the poles of the system or the characteristics equation of the system. And characteristics equation of the system, it basically defines all the characteristics of your given system, like your settling time, your maximum peak overshoot. Okay, all the parameters are defined by your characteristics equation or the location of the poles, and we can get the poles from the system matrix. So usually your system matrix, it's a square matrix. Okay, it's a square matrix always. So we can have all the operations of square matrix in this matrix A. Now what is this B matrix? So B matrix, we have seen its order, it is n cross m. So B matrix is known as your input matrix. Okay, it is known as your input matrix, and basically this matrix B, it gives us the relation between states and your input. Okay, what is the relationship between the states and the input? That is given over here. Next we have a C matrix. So you can see its order is P cross N. So this is known as what? This is known as your output matrix. Okay, output matrix. So this matrix basically defines the relationship between the output and your states. Okay, so output matrix basically defines your, means it gives us the relationship between the output and the states. Now the last matrix we have is D matrix. So its order is what? It is P cross M. So this matrix is known as transmission matrix, and it gives us the relationship between output and input. What is the direct relationship between the output and the input? It is given by what? It is given by the transmission matrix. Okay, usually you are going to see in the all the question, most of the question, you can say 99% of the question, D is equal to 0, because in your real life system there is no direct relationship between input and output. Okay, there is no direct relationship. There is always a system that acts on your input to give us output. There is no direct relationship usually in a system that if you give input directly, your output is affected without the system. Okay, so usually you are going to see that D is 0. Now let me show you the relationship. Okay, so if your system matrix, it is defined by your n cross n, or it is defined by your A matrix, you can say. Okay, so this is defined by your A matrix n cross n. Input, it is it is your defined by U matrix, so it is M cross 1, and output is what? It is defined by Y matrix and it has dimension P cross 1. So now the basic relationship between input and system, it is given by your B matrix, and the relationship between system and output, it is given by the C matrix. Okay, C matrix. And direct relationship between input, you can see I had told that basically there will be no system in between. So direct relationship between input and output, it is given by what? It is given by your D matrix. Okay, so you can see over here that this is the basic relationship between A, B, C and D matrix. Okay, so now let us talk about the block diagram of the state variable representation. So over here you have x dot is equal to ax plus bu and y is equal to cx plus du. So how do we actually do it? So look over here. So first of all, let me make this x dot and x. Okay, if somehow we are able to do that, we will be getting all the relationship. So we know if this place is x dot. Okay, so let me write over here, if this is x dot, so if I pass it through integrator, x dot means what? It is basically dx by dt. Okay, this is what is meant. So now if I pass it through integrator, so integrator means 1 by s, so it will become x. Now look over here, basically x dot is equal to ax. So now what I am going to do, I am going to feed this x through a block A that has gain A. Okay, so if this is A, so you can see now I have ax over here. Okay, so this is ax plus bu also we have. Okay, so let us make one more block to which we are giving the input. So this is b, over here we have u, over here also this is plus. So now you can see this x dot is equal to ax plus bu. Now we have y is equal to cx plus du. So this is over here we have x. So now if we pass it through c, so you can see this is c. So over here, if I give this to one of the adder once again, okay, so this is y is equal to, over here we have cx. I need du also, so u is over here. So what I will do, I will take one takeoff point and add it to a, means give it to a block. So this will be d and this will be added over here. So this is plus. So you can see this is what? This is du we have. So now this is your y. Okay, so this is the basic block diagram of a state variable representation. You can see basically this is what? X dot is equal to ax plus bu and y is equal to cx plus du. Okay, so this we have actually got over here. Okay, so now let us see how do we form the state model from your transfer function. Okay, let us see this, that basically how we do the state model from your transfer function. So if suppose we have a transfer function, it looks like this. So how do we form the state model? Okay, so let us see. Basically here what is the order of the system? or order of the transfer function. So order is basically what? So let me write this as ys by us. So this is equal to 10 by s plus 2. So order means what? The maximum number of poles in the system or the highest power of your denominator in the transfer function. So that you can see is 1. Order of transfer function is equal to 1, and whatever is the order of transfer function, same will be the number of state variable. So number of state variable is equal to the order of system. Okay, so now over here you can see that this we have got. So now let us cross multiply. So for this particular case, when your numerator is just a number and we have a equation of s in the denominator, at that time we are going to use this approach. So this will be sys plus 2ys is equal to 10 u of s. Okay, so we have this. Now let us assume what? Y is equal to x. Okay, let us assume y is equal to x. Or if you see this equation, this is basically what? This is equal to dy by dt plus 2y is equal to 10 u of t. Okay, I have simply taken what? I have simply taken your inverse Laplace transform. Okay, so here you can even write y of t, y of t. It's okay, you can even skip. Okay, let it be like this. So if I take y is equal to x, that means x dot is equal to what? Dy by dx. So let this be equation 1, and you can see dy by dx is equal to, means I can write this equation as, sorry, dy by dx I wrote. So this will be dy by dt, because I am differentiating with respect to time. So dy by dt is equal to 10u minus 2y, and y I can replace using x. So I will be writing x. So this is equation 2. Okay, and dy by dt I can replace it as x dot. So x dot is equal to 10u minus 2x. Now if you compare this, so we know x dot is equal to ax plus bu and y is equal to cx plus du. So this we know. So now comparing with this, you can see I can write this in matrix form. So this is 10u, don't consider, means I have written it like 100. Okay, so let me write it properly. 10u and this is u. Okay, so if you compare, you can write it as x dot, so this is 1 cross 1 is equal to, a is minus 2 over here, 1 cross 1, x 1 cross 1 plus 10 1 cross 1, u also 1 cross 1, and y it is equal to what? So you can see y is equal to x. So 1 cross 1 is equal to 1 into x, and there is no relationship between input and output directly, so you are not going to write anything. So this is what? This is the state variable representation of this transfer function. Okay, so now with the help of this transfer function, if I want to draw the Sfg model, so how am I going to do that? So for that you need to take this two expression. Okay, this expression and this one. Okay, so how do we basically form the Sfg from your state transfer, means state transition model? So we have what? X dot is equal to 10u minus 2x and y is equal to x. Okay, so this we have. So first thing first, you have to draw this x dot and x. Okay, so let me mark this as x dot. If I pass it through integrator, so over here we have x. So you can see y is equal to x. So let us write this as y, this as 1, and x dot is equal to what? Minus 2x. So write this minus 2 plus 10u. So right over here 10, and this is u. So you can now see x dot is equal to 10u minus 2x and y is equal to x. So this is the SFG of the given diagram, and from this SFG, if you calculate the transfer function, so y by u is equal to what? If you calculate, so forward path, you can see over here it is 10 by s, okay, and over here means your this thing what means coefficient of the forward path, okay, so I forgot the term actually. So coefficient of the forward path, it is what? It is 1, because if I remove this, okay, if I remove this path, okay, there are no loops left over here, okay, so 1 minus loop gain, so there is only one loop, that is this, so this will be minus 2 by s, so this will be 10 by s divided by 1 plus 2 by s, so if you take LCM, this will be 10 by s plus 2. So this is the transfer function that we have taken initially, okay. So now let us take one more example over here. So this is your, you can see now, order is 2. So if order is 2, so number of state variable is how many? Number of state variable is also 2 over here. See, previously state variable was 1, so I had taken x over here, but now as there are 2 state variables, I am going to take first as x1, another as x2. So these are the 2 state variables that we have in this particular case. So now again let us write Ts as ys by us. So this will be 100 divided by s square plus 3s plus 2. So if you cross multiply, this will be s square ys plus 3s ys plus 2y of s is equal to 100 u of s. So this we have. So now if I write this, means if I take inverse Laplace transform, so this will be d square y by dt square plus 3 dy by dt plus 2y is equal to 100 u, okay, 100 u. Fine. Now let us define y is equal to x1, okay, so this is the first one, and x1 dot is equal to x2, okay. So this we have over here, that y is equal to x1 and x1 dot is equal to x2. So what is x2 dot? So x2 dot, you can see basically it will be x1 double dot, okay, x1 double dot, or that will be what? Basically x1 means x1 dot is equal to what? dx1 by dt, okay, dx1 by dt. So now over here if you see this, so basically you can see that x2 dot is equal to what? It is equal to x1 double dot. So if we have to solve this now, okay, so if we have to solve this, so now you can see what I can write. This can be written as, sorry, so I have made one mistake over here. So y is equal to x1, okay, so I should have written it simply over here. So if y is equal to x1, that means what? If I have to write dy by dt, so that I am going to write as x2, which is equal to x1 dot, okay, so this I should have written. So now if I want to write x2 dot, so x2 dot is equal to what? It is equal to d square y by dt square, okay. So over here you can see that this is basically x2 dot plus this is what? 3 dy by dt. So I can write it as 3x2 plus 2y, so that is 2x1 is equal to 100 u. So this is my equation number 1, and this I will be modifying a little bit. This is equation number 2. This you can see over here that this will be x2 dot is equal to minus 2x1 minus 3x2 minus 100u. Okay, so now from 1, 2 and 3 I can write the state model. So first equation is what? Y is equal to x1. Second equation we have over here is that x1 dot is equal to x2, and next equation we have x2 dot is equal to minus 2x1 minus 3x1 minus, sorry, this will be plus 100 na, plus 100u, plus 100u. So now if you compare, x dot is equal to ax plus bu and y is equal to cx plus du, so you can see, you can write it as x dot is equal to, so this will be 2 cross 1 as there are two states, and this over here it will be 0 1 minus 2 minus 3 x1 x2 plus 100 x1 x2. Okay, so this is 1 cross 2, this is 2 cross, sorry, so this will be what? This will be 0 comma 100, 2 cross 1, u 1 cross 1, and over here we have y is equal to 1 cross 1. So this will be 0 comma 1 x1 x2 plus 0. Okay, so this is what? This is your complete state model for the given transfer function. Okay, now if I want to write the SFG, okay, SFG, so how are we going to do that? So look over here, first start from the x2 dot. Okay, so you can see if this is x2 dot, so if I pass it through integrator, this will be x2. Okay, this is x2, and x2 is equal to what? It is equal to x1 dot. So once again, if I pass it through integrator, so I will be getting what? I will be getting x1. Okay, and y is equal to x1, you can see, so this will be y. Over here you can see x2 dot is equal to minus 2x1, so this is minus 2, and minus 3x1, so this is equal to minus 3x1, sorry, so I have minus 2x1 and over here it is minus 3x2 na, so this is minus 3x2 plus 100u. Okay, so this is u, this is 100, so this is what? This is your 100u. This is the complete your SFG for this given diagram. Okay, now the last question we have over here. Okay, last question, how are we going to solve this? So over here you can see the order of the transfer function is what? Order of transfer function, it is equal to 3. Okay, so order of transfer function 3 means state variable, number of state variables, number of state variable are also equal to 3. Okay, number of state variable are also equal to 3. So now basically what are the states? So they will be x1, x2 and x3. Okay, these are the three states that we have over here. So once again, ys by us is equal to what? It is equal to 10 divided by s cube minus 3s square plus 2s minus 10. So I will even show you the shortcut trick of writing such kind of transfer function in your state model. So this will be s cube y of s minus 3s square y of s plus 2s y of s minus 10 y of s is equal to 10 u of s. So this is d cube y by dt cube minus 3d square y by dt square plus 2 dy by dt minus 10y is equal to 10 u of t, or you can simply write u also. Okay, so now very quickly let us write. So if x1 is equal to y, then x2 is equal to x1 dot and x3 is equal to x2 dot. Okay, so then we can write what? X3 dot is equal to what? It will be equal to x2 double dot or x1 triple dot. Okay, and x1 is equal to what? It is equal to y. So this will be d cube y by dt. So you can write this as x3 dot minus, you can see this is what? This is square. So this you can write it as what? You can write it as minus 3 x3. Why? Because it is actually equal to x2 dot. Or I should write it more clearly for you guys because you are learning. So x1 is equal to this. I told what? X2 dot is equal to x1. Okay, so sorry, so x2 is equal to x1 dot, so this is equal to dy by dt. x3 dot is equal to x2, so that means what? X2 is already this, so x3 dot will be what? It will be d square y by dt. Sorry, x3 is equal to x2 dot, so this will be d square y by dt square. So x3 dot is equal to what? So this will be d cube y by dt cube. Okay, so now you can see basically d square y by dt, that is x3 plus 2 dy by dt is x2 minus 10y. So y is equal to x1 is equal to 10u. So now you can see this is my equation number 1, equation number 2, and this is equation number 3, and this is equation number 4. So x3 dot is equal to 10x1 minus 2x2 plus 3x3 plus 10u. So now if you have to write the state model, so you can write it from this 3 equations present over here. So x dot, so this will be 3 cross 1 is equal to A matrix will be 3 cross 3, as order is over here, means number of state variables are 3, so order of A will be 3 cross 3. So this will be 0 1 0 0 0 1. Okay, so how am I able to write this? So look over here, x1 x2 x3, this is already fixed. So x1 dot is equal to what? X1 dot is equal to x2, you can see x2 dot is equal to x3 and x3 dot is equal to this. So this I am going to write as 10 minus 2 plus 3 over here, plus input is 0 0 10 u, and y is equal to what? It is equal to 0 0 1 x. Okay, so this is how basically we write. So this is 3 cross 1, this is 1 cross 3, this is 3 cross 3, 3 cross 1, 3 cross 1, 1 cross 1. Okay, so now you can see basically we have got this. Now what is the shortcut way of writing such kind of transfer function? So now look over here, whenever you have transfer function in which your numerator is constant and denominator is having all the power of s. Okay, so how do we basically write the means the state model? So over here this is third order, so you are going to write x1 x2 x3 is equal to, so always remember in such type of cases, okay, so x1 is equal to y, x2 is equal to x1 dot, and x3 is equal to x2 dot, like this we have. Okay, so always this will be 0 1 0, next will be 0 0 1, and the last row you have to start it from the opposite side, means from your right to left along with the opposite sign. Okay, opposite sign. So here you can see minus 10, so here you are going to write plus 10. Here it is plus 2, so you are going to write minus 2. Here it is minus 3, so you are going to write plus 3. x1, x2, x3 plus. Now whatever is the input, you have to apply it to this x3 only. So 0, 0, 10 u, and y is equal to always this form 0, 0, 1, means you are always going to take output from, sorry, so this will be always 1, 1, 0. Okay, why? Because output you can see it, you are always taking from x1, so it will be like this, x1, x2, x3. Okay, so this is what, this is the shortcut way in which you can even calculate the same thing. You can see over here that we have got, okay, so my bad, I have done the same mistake over here also. So this will be what? This will be your 1, 0, 0. Okay, so this is how you write the shortcut method. Okay, so now this is another pattern of question that we have over here. You can see over here that in the numerator also we have a equation of s rather than having a constant number. So how do we solve such type of problem? Okay, how do we form the state model? So if you look over here, we write ys by us. So this will be equal to 2s plus 7 divided by s square plus 3s plus 2. Cross multiplying, so this will be s square ys plus 3s ys plus 2y of s is equal to 2s us plus 7 u of s. So now if you write the inverse Laplace transform, you can see at this point you will be having 2 du by dt. Now what is this? This is not defined in our state model, so we cannot use the previous method for such type of question. So what we basically do over here, we assume s to the power 0 means a constant number. So I can write even like a const x1, let it be denoted by a constant number k. It can be 1, 2, 3, 4, 5, 6, any constant number. Let us define it with x1. And x2 is equal to what? It is equal to your s to the power 1. Okay, s to the power 1. And you can see basically if you differentiate this, so let us write over here. So x2 dot will be equal to what? x2 dot, it will be equal to your, means you can see over here, so this is s1, so this will be d by dt. So if you take x2 dot, so basically you are differentiating once again, so this will be d square by dt square. So this is x2. Now what about x1 dot? So if you take x1 dot, so it will be what? It will be equal to, so here you can see this is constant, so that will be d by dt, so that is equal to x2. Okay, so this is your x1 dot. So now you can write over here ys is equal to 2s plus 7 and u of s is equal to s square plus 3s plus 2. Now if you look at this expression, so take inverse Laplace, so y of t is equal to 2s. So s is means this is actually what? 2x2 plus 7x1. And from this expression, so u of t is equal to s square is x2 dot plus this will be 3x2 plus 2x1. So you can write x2 dot as what? It will be minus 2x1 minus 3x2 is equal, plus u, and x1 dot is equal to what? x1 dot is equal to x2 we already have, and y is equal to, we have over here 7x plus 7x1 plus 2x2. So I can form what? I can form the state variable model. So it will look something like 0 1, and this will be minus 2 minus 3 x1 x2 plus this will be what? 0 1 u, and y over here it will be equal to 7 2 x1 x2. So now here also we have a shortcut trick like we have just now previously. So the last row of your A, it will be basically written from right to left along with opposite sign, okay, and your C matrix will be also written from right to left. You can see 7 2, but over here there will not be any sign change, okay, there will not be any sign change. So look, one more question we have over here. So here you can see basically Ts is equal to what? It is s to the power 1, s to the power 0 is missing, so I can write 0 s to the power 0 divided by s square plus 5s plus 1. So if I have to write directly, so A matrix will be equal to 0 1. So opposite from here you are going to write, so that will be minus 1 minus 5 plus U means B matrix will be always 0 1, okay, it will be always 0 1. U means I should have written x dot is equal to, over here also we have x, and Y matrix it will be what? So you have to write from this direction, so this will be 0 1 x, okay. So this you are going to solve like the method I have shown you. So with this method you are going to solve. Similarly, if you want to write over here, so x dot will be equal to, so over here you are going to write 0 1 0 0 0 1, and opposite you have to write, so this will be minus 2 minus 3 minus 4 x1 x2 x3 plus over here 0 0 1 u, and y is equal to, so from this direction you are going to write, so that will be 1 1 1 x1 x2 x3, okay. So this you are going to write. So now we have what? We have state variable representation from SFG. So how are you going to write a state variable representation when you have a given SFG? Okay. So look over here, whenever you have such kind of question, you are always going to start from the last node. First, by looking in the SFG, what is the order of the system? So order of system is equal to the number of integrators that we have in the system, that is it. So order is equal to 3, okay. So now if order is equal to 3, there will be 3 states. So this point is equal to x3 dot. So obviously this is going to be x3, which is equal to x2 dot. This point, it will be equal to x2, which is equal to x1 dot, and this point is what? It is equal to x1, okay. This is equal to x1. So now if you check, so writing from here, x3 dot is equal to, so this should have been u, so 2u minus 2x3 minus 4x2 minus 6x1, and you have values of x3 dot means x2 dot is equal to x3 and x1 dot is equal to x2. You have this, and this value is y. So y is equal to, you can see what, that it is equal to 4x1 plus 8x2. So now if you want to form the state variable matrix, so that will be what? X dot is equal to, so you can see you have to write 0 1 0 0 0 1, and over here if you write, so this will be minus 6 minus 4 minus 2, minus 6 minus 4 minus 2, x1 x2 x3 plus 0, means over here u we have at this point only, so 0 0 2 u, and y is equal to, we have 480x. Okay, so this is the state model for this specific SFG. Now similarly we have one more over here. Now it depends on the question whether you want to take x1 dot over here and this as x1, this as x2 dot and this as x2, and over here if you want to take x3 dot and this as x3, then you will get a separate kind of state variable model. If you wanted to take like over here this as x3 dot and this as x3, this as x2 dot and this as x2, this as x1 dot and this as x1, you will get a different state model. Okay, so it depends basically. So I am going to take this as x1, this as x1, this as x2 dot, this as x2, this as x3 dot and this as x3. Okay, so now if you see, x1 means x1 dot is equal to what? It is equal to minus 4x1, and from here we have 10x2 plus 10x2. x2 dot is equal to what? x2 dot, so this is u, this is y, so 3u minus 8x2. Okay, so this we have at x2, and for x3 dot we have 6u, and from here we have minus 12x3. Okay, so this we have, and y is equal to, you can see what it is equal to, 5x1 plus 10x2 plus 10x3. So now if you want to write the state model, you have the state equation, you can write it. Okay, so I am not doing it anymore. So the next thing we have over here is how to recover a transfer function from a state variable representation. Okay, so if I want to do this, we have the state variable representation like this. So these are time domain equation, so I have to take Laplace transform. So if I take, this will be Sx of s is equal to a x of s plus b u of s, this will be y of s is equal to c x of s plus d u of s. Okay, so over here I can take x of s common to this side, so this will be what? Si minus a, because a is a matrix of n cross n, and over here we don't have any matrix, this is a vector, so I cannot subtract a vector from a matrix. I need to basically do what? I have to subtract a matrix from a matrix, so this will be Si minus a xs is equal to b u of s, and I can write xs is equal to Si minus a inverse b u of s. Okay, I can write it like this. So at this place I will be substituting the value of xs, so this will be equal to y of s is equal to c Si minus a inverse x of s b u of s plus d u of s. So I can write this as y of s is equal to c Si minus a inverse b, okay, plus d u of s. Okay, so we are going to write this. So you can see what? That basically ys by us is equal to what? It is equal to c Si minus A inverse B plus D. Now usually what happens that in most of the question D is equal to 0. So what happens that sometimes student while solving question they skip the D, but remember in the formula there is always D, so never forget to write D while you are practicing the questions. Okay, so D is there. So this is the formula for transfer function using the state variable representation. Now basically we have the solution of your state space equation. Okay, solution of state space equation. So let us see what do we mean by the solution of the state space equation. So any differential equation, see basically this is your set of differential equation. We have actually defined your transfer function with a set of differential equations, and we are doing what? We are making it your state variable representation. So any means your differential equation, what we have basically solutions. Okay, so we have solution of differential equation. Like in your mathematics you might have seen that we have what? We have your complementary function and particular integral. Similarly in your control system also we have two kinds of thing. So the first one that we have over here, it is known as what? It is known as your zero input response, and the second we have, it is what? Zero state response. Okay, zero input response, zero state response. So let us try to calculate one by one what are these. So first is what? Zero input response. So zero input response, input is 0. Okay, input is 0, or you can write u is equal to 0. So that means our state equation will become x dot is equal to ax plus bu. So u is 0, so that is why not writing, and y is equal to cx plus du. So u 0, so that is why it will not exist. So now if we take Laplace equation, so remember over here input is 0, initial states are not 0. So s, see over here means in this case it should have also been s of xs minus x of 0, but remember we are writing the transfer function. For writing the transfer function initial values are 0. Okay, so that is why I have assumed x of 0 as 0 only. But here you cannot assume so, or else how will you get the response if you don't have anything? So this will be s of xs minus x of 0 is equal to a x of s, and y of s is equal to c x of s. So if you solve this, so this will be si minus a inverse xs is equal to x of 0. Okay, sorry, si minus a will be over here. So xs is equal to what? Xs is equal to si minus a inverse x of 0. Okay, si minus a x of 0, or this is basically what? This is known as your state equation. So at the moment I am not writing y of s, it is not required. Means once we have the 0 input response and 0 state response, so the total x of s will be the contribution of 0 input responses plus 0 state responses. So we can at the end write the output for that using this equation, y is equal to cx plus du. But first let us try to find out this x. So we have found this xs, and this is what? This is your 0 input response equation we have found out. Okay, now what is this si minus a inverse? Okay, what is this si minus a inverse? So this si minus a inverse, it is denoted by phi of s. Okay, so this is known as your resolvent matrix. Okay, resolvent matrix. Now Also, if you take the inverse Laplace transform of this, so this will be phi of t. So phi of t is basically known as what? It is known as your state transition matrix. Okay, so this is known as what? This is known as your state transition matrix. So phi of t, if you take the inverse, means this is what? 1 divided by si minus a. So if you take inverse Laplace of this, so this will be what? E to the power at, where a is what? It is your in the matrix. So remember, phi of t is equal to e to the power at. So this is what? This is your state transition matrix. Now there are few properties of state transition matrix that we need to study, and after that we are going to see your zero state response. Okay, so properties of state transition matrix. So the first property is what? If phi of t is equal to e to the power at, so that means phi of 0 is equal to e to the power 0, so that is 1. And this is basically a matrix. So in matrix representation, 1 is actually equal to I matrix, and the order of this means phi of t, it is actually n cross n. Why? Because phi of s, it will be n cross n. So obviously phi of t will be also n cross n. So that is why this will be n cross n. Okay, n cross n. So next expression is what? Phi, if we have phi of t is equal to e to the power at, then phi dash t is equal to what? It is equal to a e to the power at. So now if I put 0 over here, so this will be equal to a e to the power 0. So this will come out to be a. So this is also one very important property that you need to know, that phi dash 0, it is actually going to give you what? It is going to give you the state matrix. Okay. So the next property that we have over here is that if phi means phi of kt, it is actually equal to phi kt. So how we derive this? So basically phi of t is equal to e to the power at. So phi of kt, okay, so instead of t I am putting kt, so this will be equal to what? E to the power a kt. So I can even write this as e to the power t k. So this will be what? Phi of t k. Okay, so we are getting this. So basically this will be what? Phi of k t. Okay. So these are the important properties that we need to know. Okay, so there is one more property that might be useful. So that is, so this is basically derived from here only. Okay. So if k, value of k is -1, so phi inverse t is equal to phi of minus t. So this is derived from here only, from the third property only. Fourth property is also derived. Now case 2. Case 2 is what? The case 1 is 0 response. Now what is this zero state response? Let us try to derive. So just give me a minute. So zero state response. Now this time our initial conditions are 0. Okay, initial conditions are 0. Input is not equal to 0. So x dot is equal to ax plus bu. If you take Laplace transform, so this will be sxs minus x of 0. So as it is, states are 0, so that is why we are not going to write it. So this will be axs plus bus. So x of s common, so this will be si minus a is equal to b u of s. So xs is equal to what? So this is equal to si minus a inverse b u of s, or you can even write this as phi of s b u of s. So this is x ZSR. Okay, so we have ZIR, we have ZSR. So x whole means complete is what? It is x ZSR plus x ZIR. So this will be equal to what? So ZSR we have already means ZIR first let us write. So that is equal to means your, if you go and check, so we have written over here, where is that? So over here we have written, so that is equal to what? Phi of s dot x of 0 plus phi of s b u of s. So usually I prefer to write it in this form only because it is quite easier to solve this, okay? Or else what happens if you want to write it in time domain? So this will be what? X of t is equal to phi of t, so that will be e to the power at, okay, x of 0 plus, now this over here phi of s b u s, over here now you will be having convolution, okay. So this will be b u of tau phi of t minus tau d tau, okay. So this will be basically a convolution. So I don't usually prefer this one because it is quite complex and you might forget. So this is the best way in which we can actually write, okay. So we have your excess over here. Now the next concept that we have, it is basically of your controllability and your observability. Now what do we mean by the name controllability and observability? So what are we trying to control over here? Okay, so controllability basically defines the control of input, over the states is known as controllability, okay. So what I told, the control of input over the states is known as controllability, okay. So controllability is basically the ability of the input to affect the state variable of the system, okay. State variable of the system is known as controllability. What I said, controllability is the ability of the input to basically affect the state variable is known as controllability, okay. So there is one Kalman test for controllability. The only thing you need to remember is this Kalman test for controllability. So if your state variable model is something like this, okay. So now you can see over here that QC matrix is formed by B dot AB dot A square B dot, this will be till AN minus 1B, okay. So this will be what? This will be your controllability matrix. Now the system will be completely controllable if your QC means determinant of QC matrix is not equal to 0, then it will be completely controllable. And if QC matrix means determinant of QC matrix comes out to be 0, then it will not be controllable matrix. So this is what we have to remember for our HAL or PSU exams, okay. So next we have over here is observability. Just like controllability was the ability of the input to basically do what? To affect the state variable. Similarly, observability is what? Observability is the ability of output, okay. Ability of what? It is the ability of the, it is the ability of state variable to affect the output. So here basically what? Your input was affecting the state variable. Observability means what? Your state variable will affect the output. So over here also we have the Kalman matrix. So it is formed by your C transpose, A transpose, C transpose, similarly till A transpose n minus 1 C transpose. Okay. Now, if your determinant of Q transpose is not equal to 0, you will say the system is observable. If it is a singular matrix, that means what? Determinant is equal to 0, you will say that your system is unobservable. Okay, it is your unobservable. So basically, if you go and see, so if we have a system over here, so system is defined by A matrix, we have inputs over here, we have output. So input is defined by B matrix and output is defined by your C matrix. So you can see, while we are defining controllability, okay, controllability, so we are taking your, it is something like this, B, A, B, A square B, A to the power n minus 1 B, something like this we are taking for formation of matrix. So basically, controllability defines the ability of input to affect the system or affect the states, and similarly observability is what? It is the ability of the system to affect the output. So here what we use C transpose, A transpose, C transpose, similarly like A transpose square, C transpose, like this it goes on. Okay, so here you can see observability basically defines what? It is defining your system parameter with your output. Okay, so this is what we have in your state variable state transition model, the basic theory of this. So if you guys have any doubt, you can post it in the comment section below. I will be getting back to you. And if you like the session, please press the thumbs up button and subscribe to our channel. Okay, so see you in the next session. All the best for your exam. Okay, thank you.